us. Okay, cool. All right. So our mission is to empower diverse women to excel in technology careers. Our vision, a tech industry where diverse women and historically excluded people thrive at every level. Our values focus on the mission, always remember why we're here and who we're here for, design for inclusion, make space, embody a culture of belonging, advocate for change, live leadership, champion each other. As a community, we are powerful. Journey forward, recharge, celebrate wins, break barriers. All right. Code of conduct. We are an inclusive community, and we're dedicated to providing an empowering experience for everyone who participates in or supports our community, regardless of gender, gender identity and expression, sexual orientation, ability, physical appearance, body size, race, ethnicity, age, religion, socioeconomic status, caste, creed, political affiliation, or preferred programming languages. If you would like to know more, you can go to Women Who Code Code of Conduct. Welcome, Helen. Okay, also, so we have decided to create like a series where we're doing this fundamentals, which this is late in the series, but we will do this series again. And what we have now added to the events for the New York City chapter is a coffee code break that will go over this in elite coding, like a little more structured. If you guys have been to this class before, you know that we do like a little practice session, and it's kind of it's not, I wouldn't say that it's like cohesive. It's kind of something that we go over really quickly, and kind of I think a lot of those who are more experienced in the fundamentals lead the group, so thanks to those who do that for us here in this class. But the next coffee code break, which is a little more structured, will be on binary search tree practice, and that's May 18th at 1 p.m. Another note is that tonight I will be working with binary trees, not binary search trees. All right, so you guys join me on, if you guys want to go ahead and get this out of the way now and share your LinkedIn in the chat. It's really a great way to connect coming to networking events like this. Even if it is to advance your knowledge, it's also really great to share your LinkedIn, meet other women, and practice DSAs or algorithms together or concepts together. So please do. Great. Thanks, Maylene. Share your LinkedIn in the chat. And then this is mine. I've sent the Slack channel, the Slack link, but I will send it again later on before the end of the class. Okay. So while you guys are doing that, definitely add each other on LinkedIn. We're going to move to agenda. So great. Perfect. I'm on time. So review of trees is first. We're going to review algos to traverse trees, DFS, BFS. I'm going to go over some code that is already written, and then just kind of show you in the terminal what this looks like when we get into like creating a tree and what nodes looks like and how they store data. And then we're going to build a tree, and we'll go over DFS recursion, DFS with a stack, and then we will do BFS with a queue. All right, we'll practice. So what's going to happen at 7:30, if we can stay on time, I will put you guys into breakout rooms. I have a really small practice question that you guys can review and go over, and whoever maybe just wants to take the lead, you guys can just figure it out. We're not going to go by language in this event, but next week when you do coffee code break, you will be able to get into breakout rooms with your preferred language. But today we're not. If whoever wants to, take the lead, please do. Also, please do join the breakout rooms if you can. We'll review answers and then we'll go over questions. Okay, great. Let's go ahead and move forward. All right, so trees. So trees are a data structure. Tonight we're going over binary trees, which means that you have a root, you have a child, and the difference between a binary tree, what we will go over tonight, versus the difference of a binary search tree is this. A binary tree will have a root and then a child, and the child doesn't have to be less than the root value. Okay. A binary search tree, which I can give you guys a link. You have a root, and typically to the left or the right of that node will be a lesser value than the root's value. Okay. So tonight we'll have different values, and you'll see when we build this out. They're pretty similar though in time, space, complexity, and big O. So it's okay that they'll be a bit different. Okay, so here are the terms, right? Nodes. Nodes store your data's value, whether that be numbers, strings, whatever you're wanting to store. Root. The root node is the first node in the tree. A child, a node that is directly connected to another node that is further away from the root node. Okay. Parent, that is the inverse of a child. Siblings, a group of nodes that share the same parent. And a leaf is a node with no children. All right. And I can give you guys this, I can try to figure out a way. Oh, I can email the link to this PowerPoint presentation afterwards, so you guys can access this later, because we're going to kind of move through this. Any questions so far on just the basic terms? All right, cool. So here's an explanation in a graphic format. So this is your root, which is at the top. Then you have your children, which B, D is a child of B, and H is a child. This is a subtree of a tree. And this F is a leaf node. And then the siblings are the levels, right? F and G. And the parent node is the node directly above, so the child node. All right, I'm gonna move to the next slide. Oh, okay, I see a question. Go ahead, Leah.
Hi, just a quick question for a binary tree. Is
Yeah.
there, the insertion is usually like the node, and if the node is full, then the left. If the left is full, then the right. And then once that's full, then they go to the left node again. So it's
Not
node left,
always.
right, node
No,
left,
no,
right.
no, no. You don't have to have a left
Okay.
and a right. For a binary search tree, I think you do, but I'm not sure. I haven't really, I did not go into binary search trees. I'm only doing binaries. But you can have a leaf node.
Right. But
It would be, you're asking if the insertion would be,
or
would
will
go
that
to the
depend
left.
on the
No,
implementation?
you can do to the right as well.
Okay. Okay, so because as far as I know, a binary tree is unordered. The only constraint is that any given node can have at most 2 children.
Right. Correct. All right. So we're going to move on, but that is correct.
Okay.
Thank you. All right. So big O analysis here, right? We have our basis, we have our DFS and BFS, but we'll table that for a second. Let's go over trees. Okay. Trees in general, right? And here I can share this. I don't know if I can link this to you. Hold on one second. I will send this to you in the Slack in 1 second. But trees indexing is ON. This is worst case. Insertion is ON, search is ON, deletion is ON, and space is ON log of N. Now, when it comes to what we're going through tonight with the algorithms, the traversal order for DFS is depth. The traversal order for BFS will be level. The data structure used for a DFS, and basically DFS and BFS are algorithms, right? BFS is considered a full algorithm. I'm not sure if DFS is a complete, but BFS is complete because it goes through every value. The time complexity of DFS is OV plus E, which is, oh gosh, I'm blanking on what V means right now. I think it's V plus E, which is an edge, but I think it's, yeah, it's vertices. Thank you. Or nodes. That's what I was wondering. I was like, wait, but isn't it the node? But yes, it's the vertices. Okay, and BFS is OV plus E, okay? Thank you, Larry. Yes, E is edges. So the space complexity of a DFS is OV because we're going through OV, but thanks to Larry, we're going through every node, okay? So O of V, meaning however many nodes are there or that we iterate over or through to find the value or traverse. BFS is the same, O of V. And traversing the tree is narrow and long, whereas for DFS, whereas BFS is wide and short. All right. Okay, cool. Hopefully I'm on. Okay. So for DFS, we'll go over DFS first. In this strategy, we adopt the depth as a priority so that one would start from a root and reach all the way down to certain leaf, and then back to the root to reach another branch. Best to use when you need to traverse the entire tree, okay? So here, this graphic, it shows we go all the way down to the child, and then we come all the way back up. And then we go down, left, and then we come back up. I think this graphic is pretty good. All right, moving on. So first we're going to go over, there's two types of DFS. There's recursive and there's iterative. So recursive is basically going to use the call stack, whereas when we do an iterative DFS with a tree traversal, we're going to use our own stack or a stack that we provide, right? So DFS is a special recursive algorithm, whereas backtracking is the idea, actually constraint, that gets applied to any recursive algorithms. The recursive version uses the call stack. So this is DFS post over order, DFS pre-order, DFS in order, and this is BFS. And these are the different types of traversals for DFS, recursive order, right? So post order is going from bottom, top, left to right. DFS pre-order is from top, bottom, left, right. DFS in order is left, node, right. Okay. And then BFS is left, right, top, bottom. So just keep an eye out for this. You guys take note of this because the question might be on one of these guys, the practice question. All right, a few things about DFS recursive. So if the input node value matches our target value, then return the input node. For each node of the input node, recursively call this function and return the first non-null value returned by a recursive call. And I'm going to show you guys this in the code. And if this root node has no children or their recursive calls did not return any node, then return null. Okay. Now, this is kind of cool. And I really like this graphic because it really helps show what is happening. So a DFS stack is where we are going to provide a stack in our algorithm for us to store and call these are called frontiers, which are the siblings, and then traverse through the tree. So the recursive algorithm is effectively doing something very similar, but the program call stack is implicitly used to store the path from the root to the current node. With the iterative algorithm, we need to implement a stack ourselves. So recursive is essentially doing this where it's building subtrees, but right now in this graphic, this is what it looks like with a stack. All right. Let's keep moving or else we're going to run out of time. So BFS. BFS is going to go level by level. We scan through the tree level by level, following the order of height from top to bottom. The nodes on higher level would be visited before the ones with lower levels. It's best for finding the shortest path. And we will use a queue for BFS, okay? And I like this graphic because I think it really helps show how we're using this data structure, this extra data structure. So child nodes are searched in the order they are added to the frontier, or nodes that need to be searched next. The nodes on the next level are always behind the nodes on the current level. So here you can see our queue, and then check if C is the goal. And you can see how we're using our queue first in, first out. All right, I think, let me see what the next slide is. Okay. Are there any questions right now on what we've covered? I know it was kind of fast, but are there any thoughts, any questions? All right. What we're going to do is I'm going to go ahead and stop this share. So we're going to build a tree. We'll go through a DFS algorithm. And this is to find a target. So I'm not doing any order. I'm not returning the tree, the nodes values in any order. I'm just searching the tree for a target. DFS using a stack to traverse a tree for a target, and BFS using a queue to traverse a tree for a target. And I just realized that, hold on, let me get out of view mode for this really quickly. Weird, I don't know why. Okay, there. All right, cool. So if you guys want to follow along with me, I'm going to put this in the chat. This is the code that we're working with tonight. And this code is, I've already written it out for us, so you can follow along. If you want to fork this REPL, be my guest. This is the code here. I also wanted to, you see, I wanted to let you guys know that this is written in Ruby, but if you want to translate this into another language, you can go to OpenAI, which I've showed in the past, and you can go to the playground here. Hopefully it lets me and you can go like this, and you do your tag or your backtick, and I put in Ruby code. And in this, I will do, sorry, there's like a bunch of little things. And you can just do something like this in OpenAI. Go like, if you want, do your backticks and then do JavaScript, or you can do Python. And it should write it out for you and translate this for you. So if you guys want to do that. All right, cool. All right, so I'm going to stop my share on this screen and restart on another screen really quickly, which will be my desktop. All right. Okay, cool. So right now, this is all very basic. I'm not going to add, I'm not adding any, I'm not using any algorithms or any, or like, I'm not using any methods. I'm just manually adding these right here, as you can see. So we're going to build our tree, and our tree is going to look like this. Okay. So in Ruby, we define our class node. We have add our assessors. In a binary tree, the nodes all have a value, a left, and a right. Okay. So that's what we're going to initialize here in our class node. So if I do now and add a node, and I'm going to add this node, we'll have the value of 1. You guys can see this is what our nifty little data structure looks like. Okay, so we've added a node. I've not connected these yet, right? So here's 2 with a value. I'm doing 2. You can see here. 3, and we'll do 4. All right. So now what I'm going to do is set these and build a little tree. So if I look now, I have a tree, right? We have our root. We have our 2 child nodes, and we have left, which is 2, 4, and we have 1 that has 1, which is 1 here. All right. All right, so going through, this is DFS, and this is our recursive algorithm, to where what I'm going to do is I'm taking in a node, and then I'm going to set it to a target. Okay, these are my 2 arguments. So similar to what we discussed before, in the recursive, where if the input node matches, which is happening here, we're going to return that node. Okay, if the node is nil, we're going to return nil. All right, here we're setting our left to call recursively, right? Node.net left, and we're passing in our target value. And then again, right, calling on it recursively, node.right, and target, and passing in the target. And we're going to then traverse left or right. All right. So if we go through, and I'm going to put this code in my terminal, and if I call DFS, I'm going to call it on root, and I do 42, it should give us our node. No, didn't though. Uh-oh. Something's wrong. Let me see. I have. Huh. Oh, that's why, because it didn't build. I didn't do these. Okay. I was like, wait a second. Okay, now let's look at our tree. Okay, that looks a lot better. All right, awesome. So now if I call on DFS, if I call on this algorithm and I pass in the root node and I'm looking for 42, it returns the node with the value 42. The other thing I guess you could do here is if you wanted it to just return, if the tree has this node with this value, you could return true here instead, I guess. But yeah, now if we do DFS and we pass in root and we do like -99, it's going to return nil because this doesn't exist in our tree. All right. I feel like this is going to, we have a lot. There's a question. Oh, okay. Do you need the font to, is this any better, Sherry? Can you see now, or is that, does that help, or? Oh, okay, bigger. Okay. Is that better? Does this help? Let's take this over. Okay. Okay, there. Is this good? If you want to follow along, you can also look on the REPL as well. Okay. All right. Awesome. Cool. All right. I'm sure. Let's see. Maybe I should split, but yeah, this is fine. All right. So, all right. So I really want to work. I mean, recursive is great, but I really think going through and using a stack, I wanted to go through this method in BFS using a cube because I think it's really cool the way that it works. So here, when you're creating and using a method, creating a stack, we do something very, very similar. And Anna, are you asking about the DFS here? And okay, I thought maybe I didn't need this, but you do, because we need to go through left or right. We need to do both to check if it exists on the left side or if it exists on the right. Because if you take it away, it was only returning, for me when I was doing this earlier, it was only returning the right side values. It wasn't traversing through the left, which I thought was kind of interesting. But yeah, good question. All right, so here what we do is you will go ahead and implement your stack. And let's see if I can just go ahead and show you guys what's happening, because I think this is really cool. So basically what we're going to do, if you look and you see this, you can see that we're going to, just to go over this again, we're going to put in our root node and then we're going to pop it, right? Because this is a stack and it's last in, first out. Okay, so if we kind of look at this GIF and we see what it's doing, right? All right, I'm going to come back to the code, just like you can see how we're traversing this. If you come back to the code, what we're going to do is first we're putting in our root node. And then we're going to start going through the tree until the stack is empty. And we're going to set our first, which is our root or our current, to the first element. We're going to pop that out. And then we're going to put in, I'm jumping ahead. If our current is going to then if our current matches our target, we're going to return it. We're done. We don't have to do anything else, right? If not, then we're going to append our left unless current.left is nil. And then from there, we're going to do our right, which is then we're going to append our right, cur.right, unless cur.right.nil. And so you can see that's what's happening here, right? We go through and Code Academy, I liked this GIF because I think it was really cool. And it's a good visual, but they call this frontier, which are the nodes that are being searched next. So A is pushed, it's popped, and then we're going to put in B and C, which I think I might have gotten that order wrong. I think it's, yeah, B and C, right? And then we're going to go through this and we're going to check it until we iterate through the stack until it's empty, or until we find the target. Okay. So if I do DFS stack and I put root and I do 42, it gives us 42. Awesome. And Sherry said it looks like C was pushed into I think it's last in, first out, right? For a stack. So it should be left and then right. So I think it should be left would be B and then the right node would be C. And that's what we're doing here. If you look at our code, first we're going to append, right, our left, unless left is not there. Or we're going to append our right, right? No, I don't think so. I think the drawing's right. A, B, C. We're pushing it in. B is last in, first out, right? B goes first. See how B leaves? Yeah, it does. It does. All right, I have to keep moving. Or and then at the end, if we don't find anything at all, we have to then return nil. Okay. So this is DFS stack. I've put this in, and actually I can just show you if we do DFS stack and we want to do -99, it returns no. All right, cool. Now we're going to go over BFS, and I'm a little behind time, but okay, so the difference in this case is we have our BFS return nil if node is nil, and we have our queue, and we know that for a queue we push our node, we're pushing our root node. So if we look again into BFS, and you can see A is pushed in and then it's popped out, right? And we're checking that. Then B and C are pushed in and B is popped out, right? And we're checking that. And we keep continuing to do this until we found our target, or unless we found the end or there are no other nodes, or we hit nil. So exactly the same thing that happened with a stack, but in a queue, it's first in, first out, not last in, first out, right? So we go, yes, sorry, I always get that kind of confused, but yeah. So we're going to go until the queue is empty. So we set our current, which in this case, similar to before, is our node, is our root node. And we're going to pop that out, and then we're going to check, hey, is current value equal to our target? If not, then we're going to push in the left unless it's nil. And then we're going to push in the right unless it's nil. And then we're going to continue to iterate through this and pop out in the order of first in, first out. And when we hit our current value equals our target, we're going to return that node. Okay, so here is BFS. I feel like I kind of brushed over why you would use this. So here, perfect. It's doing exactly what we want. It's returning this node for us. You could also do, like, if you wanted to, you could do like current dot, I guess, value too, if you just wanted to get the value of the node, right? And then if we do BFS, and then we do, let's say something that's not there, right? We want to do our root and -99, we get no. Awesome. So this is just like, I just wanted to give you guys some, I guess, give you methods of what it looks like to go through and use a stack in BFS and use a queue in BFS, and also recursive method. And I've given you those code examples, and you can play around with them. Like, this is everything that we do in coding is always, I mean, you know, there's many ways to do it. So if you want to change it up, be my guest and do that on your own time, and play with it and see how this is working. Go for it. I highly encourage it. Everything that we did here in the Visual Studio Code is in the REPL, which you guys can't see. Sorry. 1 second. Cool. Okay, great. Can you guys see my REPL now, or yeah? All right. Let's see. Yeah, I can, Sherry. So I will go ahead and share this with you guys in the chat. Okay. So are there any questions at this point? It's pretty basic. This isn't really, I'm really just going until this, you know, this is just DFS, BFS, and I'm also using a target here. So I'm actually looking for, you know, it to tell me whether or not this node value exists in the tree. It's, yeah, these are much lighter than shortest path, or, you know, other algorithms that are going to be much like topological sort, things like that, which are going to be more complex. But I think this is a good start. And it's kind of the way I started, was on these methods, and it really helped kind of understand what I was working with when it came to a tree. All right, we don't have much time, but the practice is, thanks, Sherry. The practice is going to be this leak code question. So I'm going to go ahead and break you guys out into breakout rooms. Please join the rooms so everyone can, so that way some rooms aren't less than others. Let's see more. Okay, I have to, sorry, this is always an interesting experience. Okay, cool. All right. So yeah, like I said before, you guys just, this really is getting you into the practice of getting into leak code, understanding what a leak code problem looks like, and playing around with it with other people in the event. All right, I am going to go ahead and open all rooms, and then let's say, what is it, 7:40, come back around maybe 7:50, maybe 7:55. Oh, and also don't overthink this problem, by the way. This is, remember the order. Yeah, okay, so I'll let you guys go to it. Good luck. Hey, everyone. Is everyone back? Let me see. Okay, cool. Did anyone want to share their, I know that was very quick, so it might not have been long enough to get to a conclusion. But did anyone want to share what they may have started, didn't finish? Any thoughts?
Breakout room number 2, I think. We did try to do a recursive solution, but
Oh yeah, that's right.
and basically, well, it didn't work. Fun fact, but
Oh, shit.
it was so just as a disclaimer, this is JavaScript. I'll just paste it over, and
Yeah, go for it. Yeah.
oops. Wait, there's
Uh,
something going on in my Zoom. I can't figure this
Oh,
out.
that's actually really, really close to what I had, Leo. Like really close. Also, for
Right.
next week's coffee code break, just if you guys want to see the difference, because I didn't go over search trees. That's actually not, that's pretty close. I can show you. Good job. How did everyone feel? Let me see if I do this. You guys can see my screen, right?
Not yet, Jesse.
No? Okay, sorry. That's why. Let me see. Okay. Okay, cool. Yeah, I had something very similar to that. Actually, oh gosh, is it? Yeah, so this was mine. I did use a stat. Did you use this? Oh no, I used it. Oh, that's why. Sorry, Leo.
You did an iterative version then.
No, but I
Oh,
do
no, that was
call on
same.
itself here. I do
Right.
use it as well. So that's what I was thinking. Yeah,
Okay.
that's
Yeah.
what I was thinking. So it seems like you were really close though. Like maybe if you had used a stack or, but yeah,
I know it could be done without having that external
it's
hold,
gotta be for sure.
but
Yeah.
I just can't. I could not remember. I always get it mixed up. Death first and breath first. So I'm just like, well,
I
no, not sorry.
the stack or queue or
The iterative versus the recursive. Like my brain is just still mixing the two algorithm styles.
yeah,
So I'll
yeah.
sort it out.
Yeah, that's why I tried to go over it, but basically, yeah, when calling iteratively, okay, is it Lakshmi or Lakshmi? Sorry if I mispronounce your name. So yeah, I like how you process each, okay, Lakshmi, sorry, I'm just, anyway.
You got it right. Yeah,
Okay,
Lakshmi.
great.
Yeah.
Okay, great. Yeah, so process each node, make check for its a leaf at each node. That's actually really smart. Yeah. But wait a minute. Are you doing left root and then right?
Yeah.
Okay.
Yeah.
But it was really close. Sorry. This was actually really like, yeah. Okay. So maybe that was a little, well, I mean, I think what I really wanted to give tonight was just like, and trees are hard, and I could have probably just like broken this up, but I did this class before. I really wanted to just go over and give you guys the code, take that code, put it in OpenAI, translate it into the language that you're most comfortable in, and like just hold on to these methods because they're the starts and they're the start and the foundation of DFS and BFS. And I can send out the like even tonight, I was going through the methods, and the visualizations like this are really helpful. And it's actually really brilliant stuff, right? Like this is so cool. We have two different data structures that we're implementing. And it's really, this is why you have to love computer science. It's like so beautiful the way that this works out, and how, the algorithm is. And I don't know, I especially love it, you know, with the visualization, because it shows in this case where we're looking for a target, how helpful this can be, right? If we're needing to find that value. I think I did share the link or also, so next week with Coffee Code Break, I think they are using a binary search tree, and kind of what Leo said earlier and what we discussed is that a binary search tree is going to be implemented differently because it is an ordered tree. And yeah, so just keep that in mind. I did go ahead and I put a link above if you guys want to look over that for next week, just in case. But yeah, we're going to try to do this for the next, I guess, the graphs. I'm not really looking forward to that, but we're going to do the same thing for graphs, which will probably be almost very similar. It'll just be a different create how we build, like the graph will be different than how we build the tree. And also, I guess, like, yeah, with traversing a tree and you can use DFS and BFS for trees and graphs. It just gets a little more complicated because graphs, you know, there's weighted, unweighted. Yeah. So I'm going to have to figure out what we're going to do for next week to keep it simple. 1 second. I'm trying to get this for you, Sherry. Okay. I'm going to give anyone who have the link. Okay. Here you go. Let me know if that works. And then if you have trouble, this is the slides. Oh no, gosh, it does this every time with Zoom. It like sends it to the person who messaged me last. Sorry, guys. This is the docs this is the presentation for tonight. So we have like a few minutes. Just to wrap up, I originally started this for 1.5 hours, but I just think it's a lot of time. And through the events that we've had through this series, it seems like a lot of people, especially beginners, it's really helped just to get basic concepts, even though I know they are basic, but just get your feet wet, and then also have that collaboration, like experience of going into LeetCode and talking about it with everyone. So it looks like I'm going to have to just open this link up. I figured that would happen. So yeah, I'm trying to structure this. It's not going to be a, I mean, I'm trying to give you resources. So like, say you come to this class and you can use the resources in this class and the slide decks, in the slides, and you can go on and continue, and see, deeper dives into this. I just want to give you like a basic, I guess, foundation. The big O, which I tried to talk about, but did not get to talk about, what is this that I went through. This is a nifty cheat sheet. I mean, we could probably do like, something else and later in a new series, but yeah. So yeah, use the links here. Thank you guys so much for coming. Are there any questions or anything that anyone wants to like talk about before they leave, or any networking, whatever you guys, any thoughts, feelings? Don't be shy. You can say whatever you want to say. Or feel free.
Just some feedback.
Yes, Miss Yao.
So I was working. Oh, sorry. No, I was working with Shifra, I think Anna and Larry, and I think what threw a lot of us off, or at least what threw me off for sure, was the fact that like we briefly went over the different types of like order, the pre-post in order. I feel like I've heard about it before and I completely didn't really understand it, and I think that maybe the coverage was a little bit too fast during the presentation. Larry was kind enough to explain it to us as a group with paint. So that was pretty nice. We spent majority of our time doing that. I feel like 15 minutes might not be enough, especially if you want collaboration. Might be possible if you try to, yeah, thanks, Larry. If you try to plow through it, if you have like a good understanding of what that was. Like I have personally, like, traversed trees before, but haven't done it with that order. I'm still not getting the question right. I'll probably take a look at it later, but I think that, that kind of threw us for a loop.
Yeah, I mean, this is like the struggle with this class is that like, is the time, the overwhelming amount of like information, and then also the choice of the leak code question. And I think like that's like something that I haven't really figured out yet. And I could have maybe chose something different, but I thought because of this, that, yeah, I did great. I did kind of just like gloss over this really quickly. So I hear that, and I hear your feedback. I guess, it's just, again, like trying to figure out how to make this work and be smooth. Maybe you just, more time would have been better as well. It's just a lot to cover in like topics where we're in trees. There's just a lot of information, and really, even this is the second time I've taught this class, and it was a lot better this time. But yeah, there's a lot to cover, and trying to figure out what to cover. I feel like I had to, so everyone didn't feel like they knew like post order, pre-order, and in order. Is that kind of like a common theme? I guess this is, I did move through it very quickly. So yeah, I'll try my best. It's just like leak code doesn't offer, I guess if I go to leak code, what is it? The problem list. It's hard to like, when you go to explore and you're looking through like the problems, it's like I try to do it. I was looking, I think I searched by binary tree. So I probably could have, but even some of these were like, let's see, I guess we could have done the same tree, but I feel like that might have, yeah. So yeah, it's just a tough thing. But next week you'll have, okay, so you guys think 90 is really what you guys want. Oh, good call, Margaret. Thank you. The mirror tree, I think might have, yeah. Well, just to see if they are, or like the same tree, something similar. Sorry, I'm just reading the chat and catching up. Yes, I will post the, you're welcome on. I will post the oh yeah. I will post the recordings and everything and get those in the Slack. So guys, please join our Slack, because this is where we really share everything. So I will post that again. Yeah, thanks for your feedback.
Jesse, I know you said that, and I think we all kind of feel it, that there was a lot of content, especially for people who, are newcomers to trees, right? I think it's a little bit overwhelming. Have you ever thought about like maybe splitting like the lecture up, maybe just do like, BFS, and then do a question that could be solved with BFS, and then DFS, like separately?
Yeah, that probably would have been a better, I think it would have been a slower way to take it for sure. Cause I feel like I got caught, here, join our Slack, everyone. I think getting caught up in like DFS, and like, it wouldn't be so bad if it's just DFS and BFS with like the extra implementation, but because DFS also has recursive, there's a lot, to go into explaining like the differences between the two and why maybe use one or the other. You can use, them interchangeably. It's just based off of preference, but yeah, that kind of, that took up a lot of time. I just wonder also, like, would it just be helpful just to like build a tree? Like that's another thought, right? Like not even traversing, but I just feel like I don't want to break it down too much to where it's too easy or too slow, but I think, okay, just build. Okay, so yes, Margaret, exactly. The other thing is that they've added in the events, guys, next week, they will have a problem that you will have a full hour to go over. And it's more of what I don't know, has anyone been to Coffee Code Break before? I know we haven't done them in a while. No. So coffee code break is a series we ran a long time ago. And when you go, you'll see that's really you guys getting into a leak code problem, going into breakout rooms and like discussing breakout room, like the code together in collaboration. I don't know if that's why every time it's always feels rushed, is I don't know that that's what I want to, like, I wanted to give a problem just to get feet wet and kind of get the practice in. But yeah, we'll figure it out. Thanks for your feedback, Yao. All right, is there anything else that you guys have any thoughts, questions, anything? All right, you guys, I think that's it. Thank you for coming. And I think we have the graphs lined up for like in 2 weeks. So if you guys want to come, please join that. I haven't posted it yet. I need to make a meetup. But yeah, please join that, right? Oh, no problem, Shifra. It's good to see everybody. And thank you so much for everyone who joins. We will most likely do another iteration of this and we will make it better. Thanks to feedback from everyone. All right, you guys, I hope you have a really lovely evening. I'll catch you later. All right. Bye, everyone. Bye. See you. Thanks, Leo. Bye. Bye, everyone. Oh, thank you. Shipper, thank you so much. That's really sweet of you. Bye, guys.